If you use divergence theorem, that would be super easy.
Yeah, because that's just one more step.
I remember when I was like, it was like 2 or 3 weeks ago, and I was looking online for YouTube, and they were like, just use divergence theorem. I was like, I haven't learned this yet. I can't use this. I know.
I had divergence theorem when they were in trouble. I'm like 18 months.
I'm pretty sure all that can do like a finite integral, right? Of one variable. We can do like a finite integral of one variable.
Okay, so
I just get into that stage.
we did the divergence theorem on Friday, and here's the web work that's due tonight at 7. This is number, what is this? Number 9. So I just want to talk about this one. So it's talking about this. This is a plane, and it goes through 0, 0, 2, 4, 0, 0, and 0, 0, 4, 0. So if we're just talking about the tetrahedron in the first octant, so easy way to draw that is just let any two variables equal 0, and then find the third value, and then that gives you the intersections of the plane with the axes. So we got 0, 0, 2, 4, 0, 0, 0, 4, 0, and they want to calculate the flux across S, where S is this closed surface, the tetrahedron. So that has 4 sides, right? It has the triangular top, and then the triangular sides, which are on the coordinate planes, right? So we want to, what would that mean, calculating the flux across S? If I want to do the flux through that closed surface, the outward flux, it would mean what? 4 flux integrals, right? So we had to parameterize each. So for each surface, S1 through S4, we'd have to parameterize it as a plane, and then find f dot ds, whether we do the f dot ru cross rv or the f dot n ds. So 4 surface integrals to do to get the flux, the outward flux through that closed surface, right? Is that using the divergence theorem to do it? No. So here's a big key on the final exam. I'm pointing this out. Oh, heads look up from their phones. Okay, so this is a big key on the final exam. If it says use the divergence theorem to calculate the flux across S, if you do this, yes, you're calculating the flux across S, but you're not using the divergence theorem. There's nothing to do with the divergence theorem. You're just calculating the flux directly. So what does it mean to use the divergence theorem? Yeah, the divergence theorem says that flux that could be calculated this way is also equal to the triple integral of what? So over the solid E of the divergence of f dv. So using that divergence theorem would mean calculating this triple integral, and by the divergence theorem it's equal to the flux integral that they asked for, the flux through that closed surface. So, calculating this, using the divergence theorem is not doing it this way. Using the divergence theorem says, oh, that's equal to this, so I'm going to calculate this instead. What does verify the divergence theorem mean? What would that mean? Do both and show that they're equal. Calculating the flux directly would mean what? Doing the 4 surface integrals. That would be calculating the flux directly. Verifying the theorem would be doing both, and using that divergence theorem to calculate the flux would mean finding the triple integral of the divergence over the solid. So I think this is easier, but there is kind of the hard aspect of this is doing that triple integral, the divergence is easy, but then those bounds and then the algebra on these triple integrals over tetrahedrons gets a little complex. So that's the one difficulty about this, the trade-off for doing the four flux integrals versus the triple integral. You're going from 0 up to solve for this for z, right? So if you do a type A triple integral, you go 0 to z equals for that plane. And then your outside double integral would be over that region there. And so the algebra gets a little ugly when you do this triple integral. So I'm not sure in the end which is actually less work. I don't know if they both have their downsides. But using the divergence theorem means calculating that triple integral and declaring it equal to the flux. Okay, questions on that? So you might keep that in mind when they ask you to keep on number 5. They said find the outward flux across the surface that is the circular cylinder and the end caps. They didn't tell you how you had to do this, so you might keep that principle in mind that we just talked about. So if you want to do the surface integral and actually add up 3 surface integrals, that's valid, but maybe there's another way. Okay, any questions on web work due tonight? Okay, so our final exam is a week from tomorrow night at 7 p.m. And this stuff that we just started working on, divergence theorem, and then this week is a big part of the final. Knowing how to do these flux integrals, knowing how to use theorems to do it a different way, super important. Okay? So you got lots of practice in the web work this week, and then there's 2 more pages of practice problems posted on Blackboard in the exam prep area. Super important. It's a big chunk of the test. So get started on that stuff early. So every day in class and every homework now is like review for the final. It's all like a big chunk of the final. So just approach it in that way, that you're not just doing the next homework assignment to get the points, but you're actually, everything we're doing now is studying for the final. Okay, so let's do the next thing, which is, we talked about flux density, we talked about the flux density, is that right?
Yeah.
So now we're talking about circulation density. Circulation density. So before we do that, let's talk about orienting a boundary to a surface. So we talked about orienting surfaces, and we talked about orienting curves. So what about bringing those together? So if we have an open surface S with a boundary C, so S is this surface in space, and then C is the boundary around it. So how's the orientation of S and C in sync, right? So we talked about those things separately, but how is the orientation of S and C in sync? Well, this is how it works. So if we did upward orientation of the surface, right? And then you looked at a little circulation around your N vectors that aligned with N. So if N is up, which way would be a positive orientation around in a little circulation around N? Counterclockwise, right? By the right-hand rule. So going around this would mean this way, right? Likewise, back here. N pointing upwards means going counterclockwise in a little circle around N. So then, as that little circulation gets close to C, C, the boundary of the whole thing, will go in the same direction as that little circulation around N. So as you're coming around close to C here, notice it's going this way, right? So when you get close to C, then the C will go that same way. So like here, it's going left to right as you get close to C. So then right there, C is also going left to right. See that? Same thing over here. In the back there, it's going, as you go around positively for N going up, counterclockwise, you're going like right to left back there. And so then back there, C would go right to left. So then everything's in sync. N upward would mean C is oriented, in this case, counterclockwise. And that agrees with what we talked about, how then the surface is always to the left. Does that make sense? So that would be, so that's simple. That example's simple. It gets a little more complicated when you have something like this. So if you just had the sleeve, if S was just the sleeve, and your C had two parts to it, like those two circles. So let's do this first. So then N, so which way for this N? Would this be counterclockwise or clockwise? Again, counterclockwise, like this. So then as you get close to the boundary C, which way right there? Left to right or right to left? Be right to left, right? And if we walked on that, so just to check it, if we walked on that, would our surface be to our left if we were walking around that? Okay, good. And then what about the one down below then? So the second part of C is down below. Again, counterclockwise for that N being positive. So now they're down there. As that circulation gets close to C, right to left or left to right? Left to right. So now down here we're going this way. So is that clockwise or counterclockwise? Depends how you're looking at it, right? But anyway, it's the other direction from the one on the top, right? The one on the top is going around this way, and then the bottom, it's going around the other way. But walking on that C, is it consistent with the surface being on our left still? Yeah. So the outward orientation of N means, an outward orientation on the N means positive C would be going this way on the top, but going this way on the bottom. And now everything agrees. The orientation's all in sync. Doesn't make sense. Okay, so recall the circulation around C was given by this integral here. And remember, we could write those, if it's a circulation integral, we could put a little circle on the integral sign. And that's just a line integral around a closed loop, right? The line integral around a closed loop is called a circulation integral. So what is circulation density? So like flux density was what? It was flux around a point per volume. Circulation density is the circulation integral per area that circulation loop encloses. So it's the same kind of concept as flux density, but it's kind of like a two-dimensional version of it. But anyway, circulation density is the strength of the circulation field chosen in a direction, say V. Okay, so what direction is V relative to the rotation? Consistent with everything that we've done. So if that circulation density is in a direction V, so say it's this way, then what direction of rotation are we talking about? In the plane orthogonal to V, right? Just like that's consistent with everything we've done all semester, right? So if you're choosing V to be circulation density, all right, so we're in a field, right? So we're in a field, and then we're at a point, and we can choose a direction v, and then we can say, according to that field, how strong is the rotation in a plane perpendicular to v? And that's what this is, the circulation of F in the direction of v, meaning in a plane perpendicular to v. And so like I said, that's the circulation around C per area inside of C, but then let that area go to 0. So this is totally analogous to the flux density principle, where we're looking at the flux out of a closed surface per volume with inside, and then let that volume shrink to 0. So this is the same thing. It's the circulation around a point per area inside as the area goes to 0. And so if we're picking up on things here, what is circulation density then? What was flux density? Remember what flux density ended up being? Divergence, right? It's the same as the divergence. So circulation density is the same thing as curl, right? And that's what we said. This is the strength of rotation at a point, right? The strength of rotation of the field at a point. So if you look at, you take a line integral, circulation, divided by how much area is in there, right? If there's a small area for a certain circulation, that's a high curl. If there's a small circulation for a huge area, that's a really small curl, right? So the smaller you get, the smaller the area gets for the same amount of circulation would be a higher curl, or higher strength of rotation. So we're taking the limit as the area inside C goes to 0 of the circulation around C per the area of C. And this is the same as the measure of the curl that we did a week or two ago. So we can choose V to be anything we want in this vector field, but now if we have a surface in the vector field, it makes sense to choose V to be the direction of n, right? So because we're going to analyze this vector field relative to S, the surface. So we're going to choose that V, the circulation density, to be the same as n, and then we're talking about what? Then there'll be the strength of rotation along S, right? Everywhere on S, because then our V direction is orthogonal to S. So it makes sense to choose V to be the direction of n for the surface. And then the circulation density in the direction n for the surface is the curl, right? So the circulation density is the curl, but in as much as in the direction of n. So it's the strength of the rotation of F in the direction of n. And that's the circulation density of the field in the direction n. So circulation density is the same as curl, and so if we want the circulation density in the direction of n, we're going to take the dot product with the curl and n, so we get as much of the curl as is in the direction of n. Okay, does this make sense? Any questions? So here's a summary. Circulation density in the direction of n is the magnitude of the curl in as much as it's in the direction of n. That's what I just said. Okay, any questions? Good on this slide. Ask me if I lost you. Okay, so that's just the same thing we had on the last slide. So let's see how this works here. So we've got our S, and S is in a vector field F. And then these are n vectors for S, right? N has to do with S. It's orthogonal to the surface. And then these blue vectors are not the vector field F, but rather the curl of F along S. Right? So remember, the curl of F is a new vector field. It's that we get from the original vector field F, and it's the rate of change of rotational rate of change of F, right? And it's a new vector field. So what is this? So for instance, this vector right here, the curl of F, is indicating that right here at this point, let's see if I can draw it, the rotation is kind of like, that's supposed to be in a plane that's orthogonal to F, right? So you imagine a plane orthogonal to that vector right there. That means that the rotation of F is in a plane like this, right? Okay, and so what are we going to do? We're going to take the curl of F dot n. So we're going to take as much of these curl vectors in the direction of n, or orthogonal to the surface. And so what this does for us is this curl gives us another way of calculating the circulation around, so this is an open surface now, and I've got a boundary around here, C, around this S. Did I get the orientation right? If n is upward, do you have the right orientation for C? Yeah, because you have the little counterclockwise rotation around each of those n vectors, and that would be consistent with C going counterclockwise in this case. So if we were to kind of like accumulate all the rotational vectors, the curl of F vectors, in as much as n across this whole surface, that would actually be the same as the circulation around the outside of the boundary. And then you kind of have to sit and think about that for a while for that to make sense. But so let's kind of walk through that. So we're going to look at one element of S with boundary delta C. So like this one over here. So a little right around here. So one element. One more try. Wow, I'm just, there we go. Okay, so here's, say, one element of the surface with a boundary delta C. And that thing is delta S, say. You take one element of that surface, it's got a boundary delta C, and its area is delta S. So the circulation of F in the direction of n, we said was this, would be the summing up all of these little delta C's around here per area. And then we can make things which is approximately, make things really small. When things get really small, then it's like a little teeny circulation around each kind of point area. And so then just solving this, we can say that that integral then is the same as the circulation density times ds. So I'm just kind of multiplying both sides by ds here. But we said the circulation density of F in the direction of n is just the curl of F dot n. So if we sum up all the little circulations around each DC, summing up all of these, that's the same as summing up all the curl of f in the direction of n times ds. And what is that? And then it's also the same as, okay, it's the same thing with a cancellation effect, right? If we were to add up all those little line integrals for every element, what would happen? The shared sides would cancel out, right? This one going this way, and then this element's coming around this way, so those shared sides would cancel out, leaving just the sides of those elements that are along the boundary that don't get canceled. So it's the same thing we saw with Green's theorem, and similar principle we saw with the divergence theorem. So summing up the circulation around each little element can be thought of in two ways. Summing up all the curl of f in the direction of n times the area, or just summing up all the edges that don't get canceled out, and that ends up being the whole boundary of the surface. So this is just by summing up all the little circulations. ds is really what? It's really the flux through the surface of the curl now, but not of f, of the curl. So this way is the flux of the curl. And this way is just our circulation line integral around the boundary. So that leads us to Stoke's theorem. So if you have an orientable open surface S with a boundary C whose orientation is determined by n, as defined by S, then the flux of the curl through that surface is the same as the circulation around the boundary. So what do we notice? Curl of f is what related to f? What kind of thing is the curl of f? It's the rate of change, right?
Yeah.
One of them, right? It's the rotational rate of change. And what is c relative to s? The boundary. C is the boundary of S. And what is this? This is what? Summing up all the little bits of rotational strength through S with the flux of the curl. And when you do that, it's equal to kind of the sum total around the boundary. Is this familiar? What is this? It's another fundamental theorem. These are all the things that are true about fundamental theorems. So is this our fourth one? So, yeah, we had the fundamental theorem of line integrals. We had Green's theorem, divergence theorem, and now Stoke's theorem. They all have these qualities, right? Accumulating bit by bit using the rate, right, is the same as kind of the net overall change in the quantity.
Ooh, it broke.
The net overall change in the quantity at the boundary, right? So that was this is the same. Does it still work without that? It still works. Okay, good. So again, accumulating bit by using the rate times a little change, right? Or little, in this case, a little element. Summing up the curl, which is the rotational strength, the flux through the surface, the flux of the curl, summing up rotational strength across the whole surface S, and rotational strength is orthogonal to that, so it's like the flux through the curl is the same as the total circulation you get around the whole boundary of that surface. Okay, any questions on that? So what would it mean to verify Stokes' theorem? Do both sides and show that they're equal. Before we get to that, let's do a different example. So I've got this vector field, which is minus 2y, 2x, 0. This is a nice illustrative example of Stokes' theorem. So if that was a little hazy, it's understandable. This is kind of hard stuff, but I think this example really helps. So here's this vector field, negative 2x, 2y, 0. Sorry, is it the other way? Yeah, negative 2y, 2x, 0, thanks. And then I'm looking at this this little circulation path, which is it's the unit circle at x equals 1. So it's the unit circle in the plane. So C1 is the unit circle in the plane, say x equals 1. So we're going to kind of look at Stokes' theorem, look at both sides of Stokes' theorem here, right? So the one side of Stokes' theorem says, let's look at the circulation around that outer boundary, right? The circulation around that outer boundary. So what vectors do we care about here for that? So I'm going to look at this side of Stokes' theorem. And this is for C1, it's the unit circle in the plane x equals 1. So what vectors do I care about then if I want to do that line integral in space? Okay, the vectors in the plane x equals 1. All of the vectors in the plane x equals 1? Yeah, so I'll show just the vectors in the plane x equals 1. But even, so that's just the kind of the planes, the vectors in the plane x equals 1. But even so, I still only care about what? The actual vectors on the points of the circle, right? Because as you go around that circle, we're going to be accumulating what? We're going to be accumulating only the vectors in as much as they're in the direction as we go around, right? That's what the dot dr is, right? Dot dr means just the parts of the vectors on C1 in the direction as of travel. And what do you predict for that line integral? John says 0. You guys agree? What do you predict for that line integral going around that? 0? Why 0? We're going to go around C1. Why do you think that line integral is 0? Why'd you say that, John?
Maybe because all the vectors are the same for 1, and so on the right side, I don't know if it's going to be negative or positive, but whatever it is, it's going to be the opposite of the other side.
So if we started here and we went like this, what would our line integral be, say for that top half? negative, right? So it'd be 0 at the beginning, but then like small negative, then bigger negative, then smaller negative. So we'd be all negative. And then what about the second half? All positive and equal and opposite, right? So it's going to be the same contributions positively that you had negatively in the first half, right? Remember doing those problems? It's important. Yeah, so that we would suspect that that line integral is going to be 0. So on the other side, and so we can do it fast, right? So what is f? So we need to what? Parameterize C1. So let's actually, I'm going to set up a series of tasks for you to do, and then we'll kind of do them all at once. So to do this line integral, you're going to have to parameterize C1. That means we'll call it R1. That means parameterizing a curve means you get one variable, right? One variable to write all the points on that curve. So you're going to C1, and then you're going to rewrite f in terms of, so f is negative 2i 2x 0, but you're going to rewrite it in terms of your parameterization, right? In terms of t. And then you're going to do the line integral. Don't start yet. So let's talk some more. Okay, I'm going to talk some more. All right. So then, what about the other side of Stokes' theorem? That says that circulation of f is the same as the flux of the curl, right? The flux of the curl. So we need an S that has C1 as its boundary. There's lots of choices, but there's one choice that's the easiest. What's the easiest choice for S to be that's such that C1 is its boundary? What's the easiest choice? So we need a surface in space that has C1 as its boundary, and we want to make this as easy as we can on ourselves. What's that? Yeah, there's a disk, right? The flat disk. So there's the plane at x equals 1. That's going to be the easiest, right? So we're going to make S1 is going to be the disk at x equals 1, or the unit disk, say. And that's going to be, so we'll call it RD. And then you get two variables to do that, right? You get a U and a V. Right? So this is parameterizing surfaces in space. You got a surface, you get two variables to do that. So you're going to write all the points, the points in space that are on that disk in terms of U and V. Okay? And then we're going to do the curl of f. All right? So the curl of f, you can calculate the curl. And let me show you what the curl of f is. So what did we say the circulation is going to be around this? 0. Now here's what the curl of f looks like. And you're going to find it and verify. This is what the curl of f looks like. And so Stokes' theorem says find the flux of that, the curl of f. And so what does that say? It says all the rotation is kind of in a horizontal plane, right? All the rotation in the vector field is horizontal. So what's the flux of that through our surface? So there's the flux vectors, right? There's the flux vectors. They all point up. So what's the total flux of those red vectors? These are the curl vectors, right? These are the curl vectors. What's the flux through that disk of those curl vectors? You should be thinking 0, right? Because there's no component of those red vectors that's like going through, right? That's orthogonal to that surface. When we do flux, we take as much of the vectors as is orthogonal to our surface in the direction of n. So since these curl vectors are straight up, they're all parallel to the surface. There's no orthogonal component to the surface, so we're going to expect this to be 0 as well. Does that make sense? So the flux of the curl is going to be 0 because there's no component of those red vectors, those curl vectors, that's orthogonal to our surface. There's no like rotational flow through the surface because all the rotation is this way. It's horizontal. So we want to do the math and show that both are 0, right? So we're gonna write find the curl of f if f is negative 2y 2x 0. And then you're going to set up the line integral. And here's a good chance to use what? We can use the dot n ds because we have a plane that's parallel to the yz plane. And that makes our life easier. So then we're going to use curl of f dot n ds. Okay, so see how much you can get done in 5 minutes while I take attendance. Okay, and here's a chance to ask each other questions if I lost you somewhere along the way. But what do you got to do? You have to parameterize C1, find f in terms of that parameterization, and do the line integral over there. Over here, you're going to parameterize the disk in terms of u and v, find the curl of f, and then set up the flux integral of the curl of f through s. Go. If you need help, ask someone. Is it right? Cosine t. 1 minus 1, right? You get 2 cosine t from 0 to 2 pi, which is 1 minus 1. 2 minus 2. Okay, how's the line integral? Is this what you got for the line integral? Some people? Yeah? Okay, cool. 0, like we thought. Okay, how about the curl of f? So that for the curl of f, ijk partial This is what you did? 0, 0, x is 0. Partial of z with respect to y, 0. Partial of x was 0. K is 2, is it 4? 0, 0, 4? And that agrees with these red vectors, right? Just all in the positive z direction. I'm showing the curl vectors for that vector field. 0, 0, 4. Okay, parameterization of that disk. All the x coordinates are 1, right? And then what are we going to use for u and v? U and v are going to mean what to parameterize all the points inside there? Yeah, we're going to need an angle. We need angle and then distance from the center, right? To get all those points. So this could be like u cosine v and u sine v. Let me actually write that out. It's a little confusing. Yeah, if you used r and theta, that's fine. So one of them has to be like distance out, radius, and the other has to be angle. That will give you all the points inside that disk. And they all have an x component, x coordinate of 1. So then we can use this kind of shortcut for the curl. What's our n going to be? 1, 0, 0. So some room down here. So we're going to have the double integral of the curl of f, which is our 004, dot 100, and we used, so this would be like du dv. It doesn't matter though, right? Because that's 0. 004.100 just gives 0. So it makes sense. Okay, now let me show you, we won't do all the algebra, but this made sense because, again, the circulation of the actual vector field, which is this, the circulation around that is the same as the flux of the curl through, this is the curl vector field, the flux of that through that, they're both 0. Now what if you had instead, go back to the original vector field, and what if we had a circle here at 0, 1, at z equals 1? So let's think about both sides of Stokes' theorem in this case. So first of all we care about are the vectors where? Along that path, right? Or in z equals 1. So now let's look at this circulation integral around that boundary. What do you expect? 0, positive, or negative? Positive. Because you're always going in the direction the vectors are pointing, right? You're going to get positive circulation around that boundary. And what was our flux again? Sorry, what was our curl again? What about the flux of the curl through that? There's the curl. What about the flux through that? Positive, 0, or negative? Positive, right? So your circulation around the boundary of the circulation of f around the boundary was positive, and so then the curl is up. So the flux of the curl is going to be orthogonal to that surface and go right through and give you a positive flux as well. And those will end up being the same value. You can do the same thing again. Parameterize the circle. Find the circulation around that circle. It's going to give us a positive value. Do the flux of the curl. So it's going to be 004 dot what? 001 now. So now we'll have an actual positive value for the flux of the curl. So using Stokes' theorem means find the other thing, right? Using Stokes' theorem to find the flux of the curl means find the circulation. Using Stokes' theorem to find the circulation means do the flux of the curl. That's what it means to use Stokes' theorem.